So problem 1 covers convection, conduction, radiation, thermal resistance networks, and natural convection. The conduction comes from the heat transfer through the supposed metal plate, the radiation comes from off the metal plate, and the convection comes from the natural convection that is calculated through concepts in 7C. That is all used for the thermal resistance network for concept 3, and that is how you start that problem. Problem 2 is just a for fun problem, doesn't really cover any topic specifically. For problem 3, it covers internal forced convection and external forced convection. This has to do with the assumption that it's flowing over a flat plate. That's the external convection. And then it is changed to what it looks like if it's flowing into a duct. That's the internal convection. And then that is all taken in the context of the thermal conductivity of the plate on the bottom, which is also a thermal resistance network. It doesn't need to be solved this way, but it can be solved this way. For the last problem, this is 4A, which is the lumped analysis. This is because the CPU is very thin, so it can be assumed to be lumped analysis, and so it's zero-dimensional heat transfer with respect to time. To solve the first problem, we first know that the Q is going to be this 50 watts, the surface area is going to be the 0.4 times 0.4, the corrected length, or the characteristic length is the 0.4 meters or 4 centimeters, the plate's going to be aluminum. The bulk property of air is going to be at 20 degrees Celsius in 1 atmosphere, and the plate is vertical. Our job is to find the T outside, or the surface temperature of the CPU. So we assume a steady state, it's 1 to heat transfer, the thermal properties are constant. We also take that the film temperature is the arithmetic average of the surface temperature and the bulk temperature. Then the convective heat transfer coefficient is the combination of heat convection and radiation, just simply adding them, and then air is also an ideal gas to get that thermal expansion coefficient. So first we do an initial guess, and that initial guess is going to give us a film temperature, and then we can pull those properties at that film temperature to find the Grashof number, which gives us the Rayleigh number, and based on this Rayleigh number, we can get this Nusselt number equation based on where this Rayleigh number is at, and that's in one of the tables. And so then you can find the H based on the Nusselt number multiplied by the thermal conductivity divided by the length. That gives you the H, and you can use that along with the H of radiation, which is through this equation right here, and you find your total resistance of air. And then your resistance of your plate is through the characteristic length divided by the thermal conductivity times the surface area, and that gives you this as your resistance. And then because they're series, you add them together, giving your R total, and you have the temperature difference from the inside of the plate to the outside, to the bulk properties, is divided by R total is that total heat flux. And then you can solve for the T inside because you know the T outside and the heat being applied, and then you can use that T inside to solve for the T outside with the resistance of the plate and the inside temperature, and it gives you this. And because it's so close to our initial guess, we can assume that our initial guess was close enough. So this is the Excel sheet I was using, and we actually used this Nusselt number, and this Nusselt number came from the simplified equation in the handout, and it gave us these values, and it gave us a slightly lower temperature, so I used that equation instead. So I stated earlier, problem 2 is just a conceptual question to kind of see what kind of fluids you might want to use for heat transfer. So then hopping right into question 3, we know that we're going to be using some sort of water cooling system to cool down the PC, and we're going to find the necessary velocity to keep the temperature at 60 degrees Celsius, but also using that velocity, if it was assumed to be internal force with heat coming up through the bottom, what would be the new surface temperature? And so we assume 60, T infinity is going to be 20, and then so that film temperature is going to be 40 degrees Celsius. And for part 1, we're going to assume external force, and this Q is going to be 250 watts, and then part 2 is going to be internal force, and that Q is going to be 50 watts, just because I was getting unreasonable answers. And this feeds into evaluating the flat plate assumption. We assume it's laminar flow because it's such low velocity, and then part 2, it's negligible heat loss from the duct itself. So we pull these properties for the film temperature, and then we can use those in these equations where we have Reynolds number is assumed to be laminar. We get this expression for the Nusselt number, and then this expression for the Reynolds number, this expression for the Prandtl number, which gets this value for the Prandtl number. And then Q is the Newton's law of cooling, and that can be substituted for this expression for H, and then Nusselt number can be replaced with this, and then Reynolds number can replace with this, so we get it in terms of velocity, and then rearranged to solve for velocity. Hopping into part 2, we find the Nusselt number is 5.33 for a duct with A over B equals 4. You find this as the heat transfer coefficient, and then using that, you can use a resistance network to find the T inside, which is a combination of this resistance and this resistance. And once again, radiation is negligible. You find this inside temperature, and then using the resistance of a plate, you can find the outside temperature through this equation right here. And this is 1/5 of the wattage, and it's also a lot bigger than the temperature seen in the first part. So the flat plate assumption is not valid. Then lastly, we can evaluate that the Reynolds number is going to be laminar because this is using the velocity we found, and this is the resulting Reynolds number. And the way I first solved it was using solver with Excel, and then I later solved it to show how it could be solved without solver on paper, and that's what this is right here. And part B is all of this stuff with the Nusselt number and relevant properties need to be used. Then for the final problem, we're going to use lumped analysis to calculate how long it'll take the chip to cool down to 25 degrees Celsius. And because it's so thin, we calculate the BO number later to validate this assumption, but we can assume lumped analysis. H and K are going to be constant, and then the driving force behind this is the external force convection by the heat transfer mechanism seen in part 1 of problem 3. So that's where we get this H value down here. So then we get an expression for theta is this, and then beta is all these properties right here. Plug them all in, find beta, and then we can plug in, solve for t, and we get a total t of 2.597 seconds. And then we go back and evaluate, and the BO number is actually 0.0381, so lumped analysis is okay. And this is a table or an Excel sheet showing how it was solved with Excel.